You might have heard of the term to galvanise. Galvanising is actually a chemical process, and what we've got here are pieces of iron metal or steel that are being coated or galvanised in a coating of zinc metal, because zinc metal is protective over iron or steel because it's more reactive. So here we have some electrolysis galvanising these, look like grates, putting a protective coating of zinc over them so that they increase their durability. Okay, so this is the start of electrolysis, and in this lesson we're going to look at electrolytic reactions. So we're going to refer to a lot of the principles we learnt when you did redox chemistry with galvanic and fuel cells. So what's in this lesson? We're going to use the use and limitations of the electrochemical series to explain or predict the products of electrolysis of particular chemicals, given their state, either as molten liquid or in aqueous solution, and knowledge of the electrode materials that are used. We're going to balance half-cell redox reactions in electrolytic cells, which is what's new, and we're going to balance overall redox reactions within those electrolytic cells. Okay, so let's recap what we've already learnt when we studied galvanic cells. Galvanic and electrolytic cells have similarities but key differences. So one thing that's true is that we have redox reactions taking place in both galvanic cells and electrolytic cells. In both cases, we have oxidation at the anode, represented by our ox here, and we have reduction at the cathode. And that's true for galvanic and electrolytic cells. In galvanic cells, we're converting chemical energy into electrical energy, and we do that by having two half cells divided up with a salt bridge and an external circuit. Cathode is the site of reduction, and it's positively charged in a galvanic cell. In electrolysis, we can have the electrodes in the same electrolyte, so we don't need to separate the electrolytes. What we do need to do is separate the products as they're produced, because the products will react spontaneously. We also, in an electrolytic cell, add in a power supply, and we still have cathode being the site of reduction, so red cat, but instead the cathode is negatively charged, whereas in a galvanic cell, the cathode is positively charged. Also, in an electrolytic cell, it's the reverse energy transformation. So we start off with electrical energy from the power supply, and we use it to produce chemical energy, or various chemicals that we want to synthesize. Okay, you might remember from when we learnt about galvanic cells and fuel cells that we came across the acronym COES. COES is a technique that is used to balance redox half equations in acidic cells, whether they're electrolysis or they're galvanic or fuel cells. So the sequence is the K stands for balance the key element, which is not oxygen or hydrogen. Oxygen we balance by adding water molecules to the side that's deficient in oxygen. Hydrogen we balance hydrogens by adding protons, which are H plus ions. Then we balance charge by adding electrons to the more positive side of the equation, because electrons obviously are negatively charged. And then the S means we add states. So if we follow those rules, we can write our half equations in acidic electrolytic cells. So for example, if we've got molten magnesium ions that are reduced to produce molten magnesium metal, we'll start off with our magnesium ions, and our product is magnesium metal. We're told that we've got molten magnesium metal, which means it's the solid that has melted. So we use the state symbol liquid. The key element, for COES, We balance the key element first, and the key element in this equation is magnesium. We start off with magnesium ions, and we end up with magnesium metal, but magnesium we've got one on each side, so that's balanced. We don't have any oxygen, so we can skip that step. We don't have any hydrogen, so we can skip that step, go straight to balancing charge. Overall, on the left side, we have 2+. On the right side, it's neutral. So we add 2 electrons to the more positive side, and then we can make sure that we've got our states, which we've already inserted. Remember that electrons don't have states. And the second example, if we have aqueous chromium-3 ions that are oxidized in acidic conditions to produce aqueous dichromate ions, Cr2O7 2-. So we'll start off by writing our conjugate redox pair on either sides of the equation. So we're starting off with chromium-3, so we're Cr3+, and we end up with our dichromate ions. So according to COES, we start off with the key element. Now we've got 1 chromium on the left, we've got 2 chromium on the right, so we need to add a coefficient of 2 in front of the chromium. So now we've balanced the key element. Next, we balance oxygen. We've got 7 oxygens on the right-hand side and none on the left-hand side, so we balance the oxygen by adding water. So we add 7 molecules of water to the left-hand side. Next, we balance hydrogen, and we do that by adding protons or hydrogen ions. We've got 7 times 2 is 14 hydrogens on the left side, so we need to add 14 protons to the right side, or 14 hydrogen ions. Now we've got the hydrogen done, we need to balance the charge. Now you need to look carefully at the ions that are there to make sure that you've got the charge right. So we've got 2 lots of 3+, which means we've got 6+ on the left side. We've got 2- here and 12+. So we've got 12+ overall on the right side. So that's the more positive side. So we need to add 6 electrons so we have the same charge on both sides. And then finally we add states. And we were told that we had aqueous chromium ions. We're reacting it with water, which is liquid. We were told that we produced aqueous dichromate ions. So they're aqueous, the protons are aqueous, and the electrons don't have states. Okay, now we're going to look at balancing half-cell reactions in alkaline conditions. In the past, we've been looking at acidic conditions, and we use something similar to COES, but we insert another step, so we call it CONES. So we've inserted the N step, and that stands for neutralisation. So let's have a look at an example. We know that we've got oxygen molecules, and they're going to be reduced. So we start off with our oxygen. There's no other key element because we've only got oxygen, so we can skip the key element. We balance oxygen by adding waters. So we add waters to the second side. So we've got 2 oxygens on the left. Now we have 2 waters on the right, so we've balanced for oxygen. Now we know that for every hydrogen atom we have, we add a proton to the opposite side. So we've got 4 hydrogen atoms, which means we've got 4 protons that we add to the left side. So now we're balanced for hydrogen. But we need to take account of the alkaline conditions. So for every hydrogen ion we have, we add the same number of hydroxide ions to both sides of the equation. So we start off with 4 hydrogen ions. We need 4 hydroxide ions, but we do the same to both sides. Now, hydrogen ions and hydroxide ions will react to form water. So they'll cancel out, and we've got 4 waters. What we now have is water on the left side and water on the right side. So we need to simplify. So if we cancel those 2 out, then we've got 2 waters on the left side. Then So that's our neutralisation, adding the hydroxide ions to form water. Then we add electrons to the more positive side. We add 4 electrons to the left side because that has no overall charge, and we want to balance the 4 minus on the right-hand side. And then, so we've balanced for a charge, and now we want to add states. So we have oxygen molecules, water liquid, and hydroxide ions aqueous. Okay, so we've balanced overall redox reactions before when we looked at galvanic cells and fuel cells. We use a similar process when we're balancing overall redox reactions in electrolytic cells. What we want to do is cancel the electrons, and also we want to simplify. So these are the following half reactions that took place in an electrolytic cell. We've got chromium ions reacting with water to produce dichromate and protons and electrons. We call that reaction 1. And we have nitrate ions that are reacting with hydrogen ions to produce HNO2 and water. We'll call that reaction 2. So the first one is our oxidation half equation, and the second one is our reduction half equation. We can use oxidation numbers, or in this case, just look at where the electrons are. If the electrons are on the right, it's oxidation. If the electrons are on the left, it's reduction. So at the moment, we can't just add the equations together and cancel the electrons. We want to cancel the electrons, but we've got 6 electrons in the first reaction and only 2 in the second reaction. So the first thing we need to do is multiply reaction 2 by 3. So we put a coefficient of 3, 9, 6, 3, and 3. So we'll call this equation 3. Now we want to add reaction 1 to reaction 3. So this is our reaction 1 and this is our reaction 3. Then what we do is we take all the reactants and we put those on the left side of the equation, and we take all the products and we put those on the right side of the equation. So we've got a very long equation here. Then we can cancel the electrons. So we've got 6 electrons on each side, so we can cancel those. But if we look carefully, we've got water molecules 7 on the left and 3 on the right. So we can cancel the 3 out on the right and be left with 4 water molecules. And we have 9 protons on the left and 14 protons on the right. So we can cancel out those 9 proteins on the left and be left with 5 protons on the right. So to simplify, we've got 2 Cr3 plus aqueous, plus 4 water molecules liquid, plus 3 nitrate ions aqueous, reacts to produce Cr2O7 2- aqueous, plus 5 protons, plus 3 HNO2 aqueous. That's our final overall redox reaction. Okay, now we're going to use the electrochemical series that we've used before, and this time we're going to use it to predict electrolytic reactions. So we're using the same electrochemical series that you've used with galvanic cells and fuel cells. Remember, the strongest oxidant is found towards the top left, and the strongest reductant is towards the bottom right. However, in electrolytic cells, the strongest oxidizing agent will be below the strongest reducing agent. So in this example, where the species that we have are Pb2+, SN2+, and water, and we consider water to be an oxidant and reductant as well. So the strongest oxidant in this case is our Pb2+, but it's below the strongest reducing agent, which is our SN2+, which is here. And anytime we've got an aqueous solution, we want to consider water. Now, we take the E0 of the top reaction and we subtract the E0 of the bottom reaction. So that's 0.2 0.28 volts, but we need more than the applied voltage to account for resistance, internal resistance in the cell. So the applied voltage must be greater than that's predicted by the electrochemical series. So we have a greater than sign plus 0.28 volts. So our two reactions would be Pb2 plus 2 electrons to produce Pb solid, that's aqueous, and Sn2 plus aqueous reacts to form Sn4 plus aqueous plus 2 electrons. There are two half reactions, and to get an overall reaction we would have Pb2 plus aqueous plus Sn2 plus aqueous react to form Pb solid and Sn4 plus aqueous. Okay, if we have molten electrolytes, then we don't have any water present. And if we have a look, if we find water in the electrochemical series, these ions can only be reduced, I should say, in the absence of water, i.e. the state must be molten. That's because water is a stronger oxidizing agent than manganese, aluminium, magnesium, sodium, calcium, potassium and lithium ions. So look at the states carefully. Now, the electrochemical series lists these as aqueous, but if we've got aqueous solution, then the water will react in preference. So we want to change the state to be molten. So if we, example, want to produce sodium metal from sodium ions, we identified the sodium reaction. So we have sodium ions, but instead of aqueous we write liquid plus an electron to produce molten sodium, or if it cools down, solid sodium. Okay, the other thing we want to look at is that if we want to electrolyse molten sodium chloride, then we'll end up producing sodium metal, but the chloride ions, the two chloride ions, will react to produce chlorine gas and 2 electrons. So by excluding water again, we're getting the next strongest reducing agent, we're getting that reaction to occur. So we're getting the molten sodium and we're producing the chlorine gas. Okay, use an electrochemical series to predict the products and the minimum voltage required to electrolyse a 1 molar solution, aqueous solution of magnesium chloride. Have a go at that question. Okay, so you need to unpack this question. We're told that we have a 1 molar solution, aqueous solution of magnesium chloride. So the first thing we want to do is identify the species that we have. Magnesium chloride, aqueous, contains magnesium ions, chloride ions, and water. So we want to locate all of those species on our electrochemical series. So we've got water here, we've got magnesium ions here, chloride ions here. Now we can see that because water is a stronger oxidizing agent than magnesium, the water is going to be reduced in preference to the magnesium. So we're not going to produce magnesium metal at all. And if we have a look, water is the strongest reducing agent as well. So we're not going to produce chlorine gas. So we can eliminate that. So we're going to produce oxygen gas, hydrogen ions, hydroxide ions, and we're going to take more than 2.06 volts. So C is the correct answer. In fact, the hydrogen ions and the hydroxide ions will react to produce water, but C is the correct answer. Okay, so we can use COEs in acidic conditions where we look for the key element, balance oxygens by adding water, balance hydrogens by adding protons, balance charge by adding electrons to the more positive side and adding states. In alkaline conditions, we can add in an extra step where we neutralise the protons or hydrogen ions by adding hydroxide ions to both sides of the equation. When we're balancing overall redox reactions, we want to cancel electrons and simplify. And that might mean simplifying the number of protons or hydrogen ions and the number of water molecules. When we're using the electrochemical series to predict redox reactions, we identify all of the species that are present, including water, and we look for the strongest oxidizing agent. So in this case, if we have sodium ions and water, this is the strongest oxidizing agent, so this will be reduced. If we have water and chloride ions, this is our strongest reducing agent, and this will be oxidized.